Hello, my name is Karina Jacobsen, and today my colleague Chris and I are going to talk to you about some of the research we are conducting under the FRA's Equipment Safety Research Program. I hope to show you how, though rare and tragic when train accidents do occur, it gives us the opportunity to understand how trains are performing and also how we might make things better. We call this area of study equipment crashworthiness. So what can we learn from train accidents? Well, first, what happens in accidents? Certain accidents may lead to injuries and fatalities from a loss of survival space or excessive forces that are imparted to the occupants, as well as the possibility of fuel fire that inhibits emergency egress. This can also occur with glazing failure, either failure to retain the occupants during a collision or derailment, or failure for them to operate in needing to get out of the train during egress. Volpe engineers are launched to investigate accidents and determine some of the causal mechanisms for injuries and fatalities. We also look at the crashworthiness performance of the existing equipment, both the structures, the glazing, the seats, the tables, and we interview passengers and crew to understand what their experience was like and what emergency egress was like. This slide shows a timeline of a selection of the severe and significant accidents we've investigated, including recently the Amtrak derailment in Montana. Although infrequent, these can have big consequences, as you can see in many of these photographs. And in general, we're trying to identify the issues that we see are repeating, such as a corner post failing on the end frame that then allows an impact object to move into the occupied volume, or seats becoming detached, or issues with glazing. So the findings of these accidents have essentially fueled the research that has been conducted. And next, I'm going to share with you what that improvement cycle looks like, how this feeds into the research, and then I'll give a summary of an example of a structural railcar improvement that has been completed and is currently in the regulations, as well as on equipment. Then Chris is going to give a deeper dive into the details of a research topic that is in the earlier stages of research. So what can we do with the accident findings? Well, this is a schematic that shows the cyclic nature of how the accidents define a problem, then it feeds into fueling research. This is where the hardcore engineering is done. So we have an image of a finite element model with a cab car end frame, as well as a complementary test that was conducted as part of the research of improving corner and collision posts and integrating the whole frame to work a little bit better at protecting against objects penetrating into the cab frame. And then once an engineering problem is demonstrated, then we can work with the working groups that develop both the standards and regulations and put it into effect. Then the next time we go out in the field and it involves equipment that has some of these improvements, we also get to see how things are getting better. So let's go through a specific example of how research has led to improving the crashworthiness of railcar designs. In accidents, we've observed that a single railcar in a train can end up taking the brunt of the impact and the damage. The photograph on the left shows an example of this. You can see that the end door of the car is located 2/3 of the way inside the car, showing how far the car crushed as a locomotive that was adjacent pushed into the occupied space. Let's see now how research ended up attacking this problem and designing an improvement. So there are two videos here. The top one shows a 30-mile-per-hour impact of a conventional train into a locomotive-led train. On the bottom, you're looking at a complementary train that has been retrofitted with crush zones, both at 30 miles per hour. On the top, you see that the conventional train overrides the locomotive as it impacts it, and it begins to see significant damage into the passenger compartment. The train on the bottom has no damage to the occupied space because each crush zone is designed to collapse in a predictable manner and absorb a large amount of collision energy equal to what you see in the conventional train, but done in a way that preserves lives. And so CEM, or crush zones, are now worked into federal regulations, and equipment is currently being designed and operated in the US. I'm going to pass the baton to Chris now to talk about glazing.
Hello, I am Severson. I'm going to continue our talk with a focus on glazing retention. First, I'm going to describe a typical glazing system used in the US trains. I'll describe the glazing retention failure mechanism, how this happens, what we've learned from accident investigations. I'll summarize the FRA-sponsored research performed by Sharma and Associates, and I will describe our additional glazing research needs. Typical glazing systems used in US trains generally use a polycarbonate or treated glass window pane encased in an aluminum frame. Gaskets and zip strips, also known as lock strips, are used to retain the windows within the car body sidewall. And these gaskets can be removed from the inside or the outside to facilitate emergency egress or access. And the picture here shows an Amtrak bi-level car that depicts the window in the side of the car with the rubber gaskets and lock strips visible from the outside. Glazing retention failures have been noted in a number of accident investigations that we've participated in. The mechanisms can vary from, so when a car derails, rolls on its side, slides on the ground, the external gaskets around the glazing can be ripped away. And additionally, when the car is sliding on its side, ballast and debris can accumulate under the window frame. In both of these modes, it can result in the windows being pushed inside the car. And when this happens, if a passenger falls onto the window opening while it's still moving, they can be fatally injured. The NTSB has come up with recommendations to improve window retention, and we are in the process of working on this issue right now. Here are some photos. The retention failure has been initiated. In this photo, you can see the gasket and zip strip have begun to partially be pulled away on the right side of the photo. And in the second photo, it indicates complete retention failure where the gasket has been separated all the way around and the window has been pushed into the car. To address the window retention issue, FRA-sponsored research that has been performed by Sharma and Associates, the first goal of this research was to identify design concepts which could be used to improve window retention. Many concepts were brainstormed, 6 were selected for further development, and 2 of these concepts were selected for testing. Here I've got a schematic of a cross-section of the window and car body sidewall, indicating the glass on top, the car body on the bottom, a purple zip strip on the inside on the left, and a gasket with an embedded zip strip on the right. The improved concept was to apply a thin sheet metal cap over the rubber exterior gasket and zip strip to prevent the ballast from ripping it out as it slid on the car. The second goal of the research was to identify different test methods that could be used to evaluate window retention. 3 concepts were selected for preliminary testing. That is a push test to determine the force required to push the window in from the outside, a pry test, which was performed to evaluate the load applied to the zip strip on the outside to remove the gasket, and a ballast drag test, which essentially combined both of these modes together. The results were that the design retrofits, while they did prolong the glazing retention, they did not prevent retention failure ultimately. And here's a photo of the ballast drag test. On the top right shows a picture of the test specimen taken from the side of an Amtrak car. The window panel was placed on its face on a ballast bed with additional weight on it, representing the weight of a car body, and it was pulled with a winch and dragged across this ballast bed. The research performed by Sharma and Associates has served as a great starting point for evaluating glazing research and retention. However, we have additional needs to further this along. First, we want to develop more prototype design concepts for positive glazing securement, that is leveraging input from our stakeholders in the industry to come up with improved designs to better retain windows in rollover situations. And we also need to develop a new safety center for glazing. Currently, there are many safety requirements imposed on glazing, but they do not address glazing retention. To do this, the steps involved would be to refine the test methods that Sharma has proposed so far to evaluate glazing retention, then to define performance requirements for these tests, and to test the prototype designs that will be developed to evaluate compliance with the draft requirements. So this is where we could use additional help, and this has been a very quick presentation, just touching on some of the highlights, but if anyone is interested in furthering this research, we would be glad to speak with you. Thank you for your attention. I look forward to the panel discussion.